All right, good morning, folks. I think we're up to day 5 of this. Man, it's only been 5 days. It feels like it's been 5 weeks of quarantine for this. I don't know about you guys. I'm starting to get a little bit cabin fever. Um, all right, let's get into yesterday's exit ticket. So I wanted to talk a good amount on the first question where you had to compare the indefinite integral of x squared versus a specific definite integral of x squared. Most of you talked notation, which is all correct and well and good, but I wanted to dive a little bit deeper into a conversation about the big differences between those. Um, Keep in mind, we started this chapter dealing with antiderivatives, and we didn't really have an interval to work on. So this is where we started. Section 4.1 was all about antiderivatives. So the integral of x squared without any limits, without any intervals, is going to be a function. It's a family of functions because we don't have this constant c known to us. If we had more information, perhaps we could find it. But even if we were able to solve for c, the integral would still evaluate down to an expression or a function, an antiderivative function. Okay, versus the definite integral from 1 to 3, that's going to come down to the area between the curve of x squared and the x-axis between the x values of 1 and 3. Now graphically I kind of drew that here as a quick reference. So that little shaded area is what we're finding the value for. So you do require an antiderivative, but you wouldn't stop there. You'd plug the values in and you come out to a value, a number. So essentially the biggest difference you want to highlight between these two types of integrals is one's going to be an expression or a function while the other is a value. And they take on very different meanings because of that. So I want to try and make that as clear and as obvious of the distinctions between these two, because even though they have the same notation, these are very different symbols with very different outcomes of evaluating. All right, moving on to the next one. So I had quite a few conversations about this one, which is good. I mean, I'm glad you guys are comfortable to reach out and email questions. So some of you already have seen this graph. I kind of been recycling it for the video here. So this curve by no means is an accurate representation of this function. Certainly not drawn to scale, but I'm exaggerating the steepness of it, the slope, so to speak, just so we can get a good visual here. Okay, so this curve is my exponential model for e to the 2x. And what we see here is from an x value of 4 to an x value of 10, we're going to split it up into 3 subintervals. Well, that covers a total of 6 units, so each subinterval is going to be 2 units wide, which is what you're seeing in the pinkish color here, the magenta. And it's a left point Riemann sum, so within each subinterval, it's the left side that's going to be raising the triangle up to the curve. So really when I say we're raising the left point, we're basically finding the output on our curve, on the function. The y coordinate at x equals 8 determines the height of this particular subinterval's rectangle. So that's going to be f of 8, or plugging in 8 and getting out your value. So the total area of this interval would be the width times f of 8. Repeating that process, the left point here being 6, we're going to plug 6 into our function, the width being 2, 2 times f of 6, and then repeating that once again, a width of 2, a left endpoint of 4, raising it, 2 times f of 4. All right, so adding these 3 expressions up is where we're now seeing the work down at the bottom here. So my Riemann sum is, I factored the 2 out, the width, because you notice they're all going to have the same width every time. So for computation's sake, you might want to see that. And I saw a good number of you actually leave this as part of the answer, where you factored this and you actually factored in a couple e's and the coefficient out as well, which is all well and good. But this was the most common answer I got, the 72 million and change. Okay? Keep in mind, this is a estimate, so it's very likely going to be inaccurate. I mean, graphically speaking, look at this. I mean, we're grossly underestimating the actual area. We're missing quite a bit of area on each of these. And it doesn't look like that much here, but this is a very steep curve. So each one of these gaps that is getting missed is pretty sizable. In fact, this one where my marker's on right now is huge, so to speak, in terms of the area left out from this estimate. Speaking of area left out, let's talk about the exact one. Hopefully you guys can see this. I don't want to zoom in and lose focus here. The exact area, the true area between the curve and the x-axis, well, that's now our definite integral of the function, which we now know back from 4.1 how to do the antiderivative. 4.3 told us plug in your endpoints, and that's where you're seeing these values here. This is an exact value. This is the mostly exact value. I rounded the decimal here. All right, so take a quick observation. 970 million versus 72 million. I chose this example not to be obnoxious with the numbers, but to really prove a point that these Riemann sums are far more accurate with more intervals. 3 intervals with the size numbers that we're dealing with is going to be a terrible estimate. I mean, look at this. This is not even close. All right, we're talking about less than 10% of the actual area. So if I wanted to be more accurate with numbers that are in the millions here, instead of only 3 intervals, I probably would want to cut this up into, this sounds like a lot, like 20 intervals to be far more accurate than where we are right now. Now, I'm not going to ask to ever have you guys compute 20 intervals, but that would be a far more accurate Riemann sum than 3. I'm not going to introduce a new lesson, but I do want to talk about what you probably already read on the course page by the time you're listening to this. Quizzes are still going to be a thing here. I know we're doing this at home, so they're not going to be ideal in terms of authentic work, but we're going to do the best we can. The Google survey today is going to include a question about online textbook. Please be honest with me. Do you have access to the textbook? Because right now, the most reliable way I can quiz is actually using the platform on the online textbook. I'm not going to count that, like what its grade gives you as the grade. I'll look at the work you submit. My goal is Monday, we're going to kind of do a trial run of using the online textbook to work out some of the bugs and to get you guys used to working through that platform. Tuesday, I'm going to do a very short mini quiz on a couple problems from 4.1 to 4.3. When I say mini quiz, we're talking 10 points at most. This is the first time we're trying this. I'm not trying to go crazy with this. It's again, this is the trial of this as a platform. So hopefully we see how this works. I'll take whatever questions you might have about this either tomorrow or Monday. But for now, for today, I want you working through the last of the homework problems and that bonus worksheet, which we're going to use as kind of work tomorrow as well. The homework is not needing to be submitted. It's homework. We don't grade homework here. You know that by now. It's more so you guys are keeping track with practice and reinforcement. 1 or 2 problems on an exit ticket is not the same as the problems that we would be doing on homework. And right now, I think the homework is far more valuable practice than the 2 questions I can sneak into these videos before they get too long. Speaking of which, I'm going to end it here. Enjoy your weekend. Relax, take a deep breath, wash your hands, and I will touch back in on Monday.